talk, session. And we have Connor and Ajmain that are going to talk about map coloring on surfaces.
Hello, I'm Connor.
I'm Ajmain. So we're going to talk about map coloring on surfaces. So we did this project last summer at Stony Brook University. So let's start talking about this. So you want to start?
Sure. So a map is an embedding of a graph into a surface such that the components of the complement of the graph are homeomorphic to disks. So for instance here, in white we have a graph embedded into the torus, your vertices and your edges, and each of the components of the complement are colored regions that are homeomorphic to disks. Each one of these is a polygon in this case.
Yeah. So in other words, you have you break your surface into regions, and then what you want is your map to be complete. So a map on the surface of genus G is complete if any two faces are adjacent. So for example, this is an example of a complete map. So it's like a tetrahedron. We have a picture. So a tetrahedron on the sphere is a complete map because you break your sphere into 4 faces, and then each face is adjacent to every other face along some edge. So a tetrahedron is a complete map. And then we say it's also maximally complete because you can't break a sphere into more than 4 regions such that every region is touching each other. So this is, so this, is this 4-color theorem?
It has to do with the 4-color theorem. And this is true of any surface. There's always a maximum number of regions you can have in a complete map on a given surface. You can only put on so many faces so that each is adjacent to each other. And the number of faces in a maximally complete map on a surface of genus G is given by the Heawood number. And it appears here.
So I can give you some calculations. So if you have genus here and the Heawood number of the genus here, then for genus 0, you have 4 faces on a maximally complete map. For genus 1, you have 7 faces, just plugging it into that formula. For 2, you have 8 faces. For 3, you have 9 faces. Right? So what this tells us is that on a genus 1 surface, you should be able to find a map with 7 colors such that every color is adjacent to every other color. And here is an example. So at the start of the project, we had known of this example. Everyone knows about the tetrahedron. And we also had a model for the 2 torus. We had 8 colors on the 2 torus. What we wanted to find was a 9-color map on the 3 torus. We didn't have a model of this at the start of the project, and the project was to find a 9-color maximally complete map on the 3 torus. And how could we do this? So first we start talking about base maps. So
the idea that we had to construct maximally complete maps on surfaces of genus this was to start with 2 complete maps on surfaces of smaller genus and remove from each of them a certain number of disks, and then identify the boundaries of these disks in pairs, one from the first surface to one from the second surface, in such a way that you would not disturb any of the adjacencies between the faces in either of the original maps, and you would create all the adjacencies you would need in this new connected map to have a maximally complete map on a surface of greater genus, higher genus.
So we can talk about base maps on the sphere. So here we have 4 different maps on the sphere. So the way you read these maps is you have a square, and then you identify sides according to which way the arrows are shown. So the left is a sphere with 2 colors. The middle left is a sphere with 3 colors, and so is the middle right. And then the right one is a sphere with 4 colors. Now this is a map of the torus, the 7-color map of the torus. you can see that it's maximally complete because if you focus on one face, you'll see that it is adjacent to 1, 2, 3, 4, 5, and then moving along underneath 6. So every hexagon is adjacent to 6 other hexagons, and you can fit all of these hexagons together to form a torus. So it's maximally complete. Yes, so a hexagon, if you identify opposite sides of the hexagon, you will get a torus, as this diagram shows. And so what we do, another way to represent the 7-color map on the torus is to start with 7 hexagons and then identify opposite sides of these hexagons so that you will get a torus. So here you have a hexagon tiling, and then you identify these 3 edges with these 3 edges, and these 3 edges with these 3 edges, and these 3 edges with these 3 edges, and then according to this diagram, you'll get a torus. Right? So this is a planar way to represent this 7-color map. We also have we also have a 6-color map on the torus, where you identify this top edge with this bottom edge, and this edge with this edge. So you're taking the 2 sides of the torus and gluing them together, and then gluing the 2 sides of the rectangle, and then gluing the 2 top edges of the rectangle together with a little bit of a twist, so that every square is adjacent to every other square. And then here is another 6-color map on the torus, where you just took this 7-color map and you shrunk one of the faces down to a point. So it turns out that these maps are complete, but they're not maximally complete. But we are going to use these complete maps to construct maximally complete maps on higher genus.
So here is another base map that we used, which is the 8-color maximally complete map on the genus 2, and this is just a representation that you get by cutting this by a plane and unfolding it like a hot dog bun. Right? Here, this, you can see this as the front of this 2 torus, and then this side as the back, and they fold up along a line down here, like a book, the 2 covers of a book.
Yes.
What about the little triangles? Are those glued together somehow?
They come together, yes.
Okay.
Yeah, so you fold it up like a folder, but then the 2 triangles come together too, so you get a genus 2 surface. Okay, so I'm going to skip over this slide, but basically it'll be explained soon. So here, now I'll present the 9-color map on the genus 3 surface. So what you start with is So you start with 7 hexagons, and you want to color them all different colors. So here we have, let's say, light blue, dark blue, yellow, green, orange, and red, and purple. Right? Okay, so we're going to connect this with a sphere with 2 colors, pink and brown. So what we're going to do, so we have a genus 1 surface and a genus 0 surface. This has 7 colors, that has 2 colors, so in total we have 9 colors. And we want to sort of connect them together so that we get a genus 3 surface with 9 colors. So what we do is we make 3 punctures here, here, and here, 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 and here. then we are going to connect this first circle with this circle, but we're going to have the pink touch here. So pink touches here, and then brown touches these two. So we just moved this. This is gonna. One. All right, and now, so what I did is I attached a tube along this boundary circle to this boundary circle, like this, and I extended the pink colors here down to the pink colors here, and the brown colors here along that tube down to the brown colors here. And then I'll do the same thing over here, pink and brown, and then pink, or it doesn't matter which way you put it here, but in brown. And then what you notice is that brown touches two, a red, orange, purple, wait. Should be these two, right? Yeah, like that. All right. So brown touches red, orange, purple. Purple, yellow, and dark blue, and also blue and green, whereas pink touches red, yellow, orange, purple, dark blue, blue, and green. So every color on this map touches every color in that map, so we've constructed a complete map with 9 colors. But what's the genus of this surface? You have a genus 1 surface here, and then a genus 0 surface here, and you've made 3 tubes between them, so now we have a genus 3 surface. So this is a maximally complete map on a genus 3 surface, and yeah. Okay.
So we did similar constructions for other base maps to get maximally complete maps on genus 3 through genus 7. And we have some of them here crocheted. We have this one on the genus 6, which is a little wild. There's a larger one in works on the genus 7 that's fairly, it's even crazier than this. Genus 5 and genus 4. And then this is the one that Ajmain just drew. This again was created from this 7-color map on the torus, which you can see in this component here of the map on the genus 3. And then from a 2-color map on the sphere, which is the center of this tripod. And these are the tubes running between the two of these base maps.
I want to ask, how much time do we have?
We can 50 more minutes.
50. Oh, okay.
So as we were coming up with these maps, one of our questions was, well, the 2 maps we had started with, this one on the sphere and this one on the torus, are very symmetric maps in that no 2 regions are distinguishable. There's an automorphism of the map that carries any one region to any other region. But this isn't true of the maps we were finding on surfaces at higher genus, and we wanted to know if we could find maps that had this property. And the first step to answering that question is to formalize this property in terms of, in the condition of regularity.
Yeah, so a regular map is a map on a surface where the automorphism group of the map is a symmetric group on the number of faces. So in other words, so for every vertex edge face triple, right, vertex edge face flag can be transformed into any other vertex edge face flag by an automorphism of the map. So for example, on the tetrahedron, you can take this face, edge, and vertex to any other face, edge, vertex by just some rotation or some rotation of the map. This one is also regular. So one such automorphism is this rotation. It takes this face to this face. Right? But to see that's regular, you can just look at this this planar diagram, and then notice that you can take every vertex, edge, face, triple to any other just by translating and perhaps flipping this whole planar diagram. So that tells you that the torus, 7-color map on the torus is a regular map. So we were wondering if there are maximally complete regular maps on surfaces of higher genus. And the reason for this is that it helps you understand these maximally complete maps. So for the torus, you only needed to consider, you only needed to prove that one face is adjacent to every other face. But because of the regularity property, every other face also has the same property. So then it helps you deduce that it's maximally it's complete. So we wanted to know, are there other regular maps on genus surfaces of higher genus which are also maximally complete?
And it turns out that the answer is no. You can only have maximally complete regular maps on genuses 0 and 1 for orientable surfaces. And to prove this, we're going to make use of a reformulation of the regularity condition for orientable surfaces. And this says that a map on an orientable surface is regular if I consider a vertex and the edges coming out of the vertex, a rotation around the vertex of one edge to the next extends to an automorphism of the whole map around every vertex. And then around every face, if I rotate about the center of a face, and I send the edges adjacent to this face, one to the next, around the face, this also extends to an automorphism of the whole map. Erase. So we first proved two lemmas about maximally complete regular maps on orientable surfaces. And the first is that they are non-redundant, which means that there are no two edges that are adjacent to the same two faces. So an instance of a redundant map, say you have three regions in the plane like this. This is region 1, 2, and 3. Here, say this is E1, edge 1, and here you have a second edge, E2. These are both edges between regions 1 and region 3, region 1 and region 3. Right? And these are redundant edges in the map. So a maximally complete regular map is non-redundant. And the second thing we proved using that is that a maximally complete regular map is trivalent. That is, at every vertex there are exactly three edges coming in. So we suppose that there were indeed a maximally complete regular map on an orientable surface of genus greater than 1. By the Hewood formula, that would mean there would be more than 7 regions in the map. So in particular, there's some region C that is adjacent to at least 4 other regions. Why? Because the map is complete. Thus, C is adjacent to every other region in the map, and there are at least 8 regions in the map. Okay? So around C, I have something that looks like this. I have a region A, a region B, and then some other region down here, and some region D. So these, we're just assuming there are 4 distinct regions around region C. And since we know a maximally complete regular map is trivalent, this is really what the picture looks like. These regions A and B are adjacent to each other. immediately after their adjacencies with C. So the first thing we say is, well, this map is complete, so region B also has to be adjacent to region D. So somewhere along the boundary of region B, there's some edge through which it's adjacent to region D. And applying the automorphism of the map that rotates the regions around B one to the next, or the edges around B one to the next, we get a rotation like this that sends region D to region A, rotating around B. And we consider what this rotation looks like on this part of the map. What happens to this sort of fork here of edges coming off of region B? And this is sent to another fork, say over here, coming off of region B, in which there must be a region A, because the rotation sends region D to region A. So you get that in your map. You have another fork like this coming off of region B, and here you have region A in your map. So the next thing you do is you consider a single counterclockwise rotation around region B of the edges adjacent to region B. And this sends region A to region C. If we look at what it does over here, that means there must be another fork like this. Let me draw it a little higher up. Coming off of region B, and there may be more edges in here. And here appears region C. And finally, we consider what happens when you rotate clockwise one step around region A. This sends region B to region C. Now, we have a fork here coming off of region A, and here's region B. And we just consider again what happens to this fork here under the rotation around A that sends B to C. And it sends this fork to another fork off of region, I'll draw it a little wider, off of region A. And here is region C again. So here you have some region E. And the question is, well, are these two distinct edges through which E is adjacent to C? If your map contains more than 8 regions, or more than 7 regions, and is complete, then E is adjacent to at least 7 other regions. Right? If you count the number of edges that appear already around region E, you have 1 from C, 2, 3, 4, 5, 6. That is, if this is one and the same edge, E is adjacent to 6 regions and no more. Right? Which contradicts that this is a complete map in which there are more than 7 regions. Right? So that means that these are 2 distinct edges through which E is adjacent to C, which is equally a contradiction because we proved earlier that a maximally complete map is a maximally complete regular map is non-redundant. So that concludes the proof that here we've shown that a maximally complete regular map has at most 7 regions, and then by the Heawood number that only leaves genus 0 and genus 1. In fact, this is a proof of a slightly stronger theorem, which is that a trivalent complete regular map has at most 7 regions. This is because really in any regular map on an orientable surface, around any face, its boundary consists of, say some sequence of edges that is non-redundant, and then the remainder of its boundary is just this sequence appearing again and again, a certain number of times. So this says that the maximum length of this non-redundant sequence can be 6.
Okay. So to summarize, we started with the question of finding maximally complete maps on a surface, and we wanted to find a maximally complete map on the genus 3 surface. And the way we were able to do that is by taking two complete base maps and then combining them in a way to get a maximally complete map on a surface of a higher genus. And then the next question was, can we understand these maps in a nice way, or are there very nice maps that are maximally complete, which we can understand by the fact that they're regular? And we were able to show that the only regular maps that are also maximally complete are the ones on the sphere and the torus.
Thank you.
Thank you.
So does that mean that if you go on a higher genus, every complete map is going to be obtained by gluing some gluing of these two elementary patterns, the way you did it for the genus 3?
That's a good question. So far, we've only been able to apply this technique of combining base maps up to genus 7, but we don't know if this technique can be extended further.
I mean, certainly if you start with some complete map, right, and you just, you take a mat knife and you cut out a face in this map. You can think of this as a one-color map on a sphere, and then, you know, a complete map of one less region on your original surface where that region's been contracted, right? And then you apply this construction and you get back to the complete map that you started with. Can you remove, you know, can you, say, pull off however many regions you want, like this? And in this way decompose it into two base maps. And we considered this, and I think the answer is yes, you can. That you can always think of a complete map as, you can decompose it into two complete maps on some surface of smaller genus connected through some number of identification.
Is that a keyword number, is it just a theoretical bound, or is there actual examples in every genus where there are some, you just don't, it's just like nobody knows how to construct them?
Yeah, so the original proof of the Hewitt conjecture by Ringel and Youngs goes through a very complicated process of describing these maps in terms of polygons. So basically this type of, okay, so this is the best picture that I have of it. So you have this hexagon, and then you have 6 hexagons around it. But you can think of any complete map on some surface as just some n-gon, or n-1 gon, and then n-1 gons around it. And then what you want to do is identify the boundary in such a way that you get the surface of the appropriate genus that you want. So yeah, you can do this by something called a rotation scheme. So for every face, you have the faces that are around it, and then for every other face, you also have the faces that are around that face. So you get a matrix, you get a whole matrix where the row tells you the cyclic permutation of the faces that are around it. So the problem reduces down to telling me what this matrix is, right? So the Ringel and Youngs do this, and they try to tell you what this rotation scheme is. So that matrix is called a rotation scheme. And the way they do this, so they separate the problem into 12 different cases by the genus. So the genus, or by the color?
By the number of regions.
Oh, by the number of regions in the map. So if your map has 7 colors, that's 7 mod 12. So the proof for the case 7 mod 12 works for this guy. And then, so at least for 7 mod 12, what you do is the first row of the matrix has a particular cyclic permutation, and then you get every other row of the matrix by adding something else. So you number the regions 1 through 7, and then you can get the other rows of the matrix just by getting the first row. So you need to know what the first row is, and they do this by providing a current graph, which is like, so a current graph, the current graph is basically a graph where you have
Sure, it's like
some direction along it, and then you read the numbers along that thing, and then you get the first row of this matrix. And so it's very hard. So like for genus 7, you have a certain graph, but then you can make this graph larger for to get the whole case mod 12.
I see. So you guys could potentially reprove this conjecture in some more concrete way. Like
Yeah, yeah.
Just building these kinds of.
And yeah, so the original proof is entirely, you need to give an entirely different proof for every case mod 12. Right. And it's very hard to understand these maps. The maps that we've created are very simple to understand because we've broken it up into 2 complete base maps. Okay.
What happens here for surfaces like with boundary or like with punctures in them? Like, is there a way you can like quantify like doing it or like? Yeah, I'm curious how they extend to like stuff like that.
Surfaces with boundary, you should be able to put on that surface.
There is another appropriate Hewitt formula for a number of boundary components, but I can't tell you what that is. Right?
Yeah, imagine you have some surface, some maximally complete map on that surface, and you cut out a disk that's just a small neighborhood of a vertex. Right? I think that should be a way for transferring between a surface without boundary and a surface with boundary.
Yeah, so there are lots of generalizations of this problem. You can talk about pairs of maps and like a map on the Earth, and then you have a complete map on the Earth, and then you have its paired regions with the maps on the Moon, and what is the maximum number of regions that color map in the Moon. Yeah, so there are lots of generalizations of this problem, and you have appropriate Hewitt numbers for each of those. Any more questions?
No, but thank you again. So now I think there is